We are finally at the climax of this course, and we are going to see the most important theorem in calculus called the fundamental theorem of calculus. It has two forms, and together it says that integration and differentiation are kind of inverse operations of each other. Let us see these two forms. The first form states that suppose there is a finite set E in AB and functions f, small f and capital F from AB to R such that A capital F is continuous on the closed interval AB, f dash of x is equal to f of x for all x in AB minus E, and C f belongs to RAB, then integral A to B f is equal to f of B minus f of A. Now, this is somewhat intuitive. A derivative we know captures small change in the function intuitively. And integral in some sense is like a generalized summation. So if we add up all the small changes in the function, we get the total change. That means the value of the function, the difference between the value of functions at the two endpoints. So that's what this theorem is saying intuitively, and we will prove that. Coming to the proof, we will assume without loss of generality that E is equal to the set A, B. Why can we assume this without loss of generality? Because suppose there are finitely many points in AB, we can split them into finite many subintervals such that all points in E are endpoints of these subintervals. Okay, so thus we can assume without loss of generality that E is equal to the set consisting of A and B. As always, we know that if f is integrable implies that for every epsilon greater than 0, there exists some delta of epsilon which is also greater than 0, such that if p dot is a partition with norm p dot less than delta of epsilon, then modulus of s of f p dot minus integral a to b f is less than epsilon. Now the idea is to represent S fp in terms of capital F, and for this we will use the mean value theorem. Let's get into the details now. Let p dot be the partition xi minus 1 to xi, comma ti. Okay. Now we apply mean value theorem for capital F to each of these on each of these subintervals xi minus 1 to xi. So we get by MVT there exists some ui in the open interval xi minus 1 to xi such that f of xi minus f of xi minus 1 is equal to f dash of ui into xi minus xi minus 1, which we know is equal to small f of ui into xi minus xi minus 1. So if we look at the partition q dot, which is given by xi minus 1 to xi comma ui, then norm of q dot is equal to norm of p dot, which we know is less than delta of epsilon. And S of f q dot is equal to summation I going from 1 to n f of ui into xi minus xi minus 1, which is equal to summation I going from 1 to n f of xi minus f of xi minus 1, which we know will keep getting cancelled, and then we get f of b minus f of a. Therefore, modulus of f of b minus f of a minus integral a to b of f is equal to modulus of s of f q dot minus integral a to b of f, which is less than epsilon, as q dot is a partition with norm less than delta of epsilon. But as this is true for an arbitrary epsilon, we get that integral a to b of f is equal to f of b minus f of a. And that completes the proof. So this is all cool if we knew that small f was a derivative of some function capital F. But what if we did not know that to begin with? Can we guess a function whose derivative will be small f? This theorem actually gives you a candidate for that. So let's try to define this function. Definition: if f is Riemann integrable, then you can define capital F of x is equal to integral a to x of f for all x in AB. And this is called the indefinite integral of f. Let us first try to understand intuitively why this is a sensible guess. If capital F dash of x is indeed equal to small f of x for all x in the closed interval AB, then integral a to x f is equal to capital F of x minus capital F of a. So if g of x was the function integral a to x f, that is equal to capital F of x minus capital F of a. Correct? And this implies that g dash of x is equal to f dash of x minus the derivative of f of a, which is a constant, right? So that is equal to 0, which is equal to f dash of x. So this tells that g dash of x is equal to f dash of x at all points, but we already know that f dash of x is equal to small f of x. Correct? So that is why this makes sense to define g of x in this fashion. And the reason why we cannot come up directly with that capital F is because we cannot really guess what capital F of A should be. So there is no natural choice for what capital F of A should be. So that is why we don't take any value. We take that the capital F of A is 0 in some sense. That's what we are doing. Now that we understand it intuitively, let us try to prove it in a more rigorous fashion. So we will first prove that this function capital F is indeed continuous. Unfortunately, capital F is not differentiable everywhere, but we can prove that it's differentiable wherever small f is continuous. Okay, and we will prove that whenever it's differentiable, then capital F, the derivative of capital F is equal to small f. So let small f belong to RAB, that means it is Riemann integrable. Then small f is bounded. That is, we can say that modulus of f of x is less than or equal to capital M for all x in the closed interval AB. If this is the case, then we have the theorem mod of capital F of x minus capital F of y is less than or equal to capital M into modulus of x minus y for all x comma y in AB. And this implies that capital F is continuous. Why does this imply that? Basically, we are saying that delta of epsilon is equal to epsilon divided by capital M. Okay? So we will prove that modulus of f of x minus f of y is less than or equal to m times modulus of x minus y. Let's see the proof of this. We know that capital F of z is equal to integral a to z of f, which by additivity theorem is equal to integral a to w of f plus integral w to z of f, which is equal to f of w plus integral w to z of f. This implies that f of z minus f of w is equal to integral w to z of f. So modulus of f of z minus f of w is equal to modulus of integral w to z of f. And if modulus of f is less than or equal to capital M, then modulus of integral w to z f is less than or equal to m into z minus w. The last inequality is a simple exercise and I leave that as a homework. With that, we have a proof that capital F is indeed continuous. Finally, if f belongs to RAB, that is f is Riemann integrable on AB, and f is continuous at C in the closed interval AB, then capital F is differentiable and f dash of C is equal to small f of C. So the basic idea of the proof is that we will show that if x belongs to closed A open B, then limit x tends to 0 plus f of C plus h minus f of C divided by h exists and is equal to f of C. And similarly, if x belongs to open A and closed B, then limit x tends to 0 minus of f of C plus h minus f of C divided by h exists. And again, this is equal to f of C. And together this will mean that limit x tends to 0 of f of C plus h minus f of C by h exists everywhere, and hence the function capital F is differentiable and its derivative is equal to f of C. The proof of the two statements are very similar, so we will prove the first statement and leave the proof of the second statement as a homework. F is continuous at C implies that for every epsilon greater than 0, there exists some delta of epsilon greater than 0 such that if C is less than or equal to x is less than or equal to C plus delta of epsilon, then f of C minus epsilon is less than f of x is less than f of C plus epsilon. So if you look at capital F of C plus h minus capital F of C, that is equal to integral a to c plus h of f minus integral a to c of f. Okay, which we know by additivity theorem that integral a to c plus h of f can be rewritten as integral a to c of f plus integral c to c plus h of f by additivity theorem. And this minus integral a to c f, which is equal to integral c to c plus h of f. So if 0 is less than h is less than delta of epsilon, then we know that f of x is greater than f of c minus epsilon and is less than f of c plus epsilon for all x in c to c plus h. This implies that integral c to c plus h of f is greater than integral of c minus epsilon, which is equal to f of c minus epsilon into h, and is less than integral of f of c plus epsilon, which is equal to f of c plus epsilon into h. But we know that integral c to c plus h of f is equal to capital F of c plus h minus capital F of c. So we get that capital F of c plus h minus capital F of c lies between small f of c minus epsilon into h and small f of c plus epsilon into h. Okay, so because of this we get that capital F of c plus h minus capital F of c divided by h minus f of c, the modulus of this is less than or equal to epsilon. Whenever h belongs to 0 to delta of epsilon. So this implies that limit h tends to 0 plus of f of c plus h minus f of c divided by h is equal to f of c. And that completes the proof.